Welcome to another Study Session Tuesday here on the Cyber Insecurity channel. Thanks for joining us for the 6th episode of our Intro to Python series. My name is Brent Eskridge. I go by DocJayde in the Discord. Just to recap, I've been a software developer, a computer science professor, and now a threat intelligence analyst. So I've programmed lots of different things, which means I have experience in making lots of different kinds of programming mistakes. But I love helping people learn not to make the same ones and make completely new ones. So if you want to connect with me on my socials, you can use !Brent. If you connect with me on LinkedIn, all I ask is that you send me a note, just letting me know what you're hoping to get out of this series. Make sure you follow me on Twitter. Every Monday, I post a algorithm of the week that we then talk about here on stream. I want to thank our moderators for being here. We have a zero tolerance policy on toxicity on the Cyber Insecurity channel. We want this to be a positive learning environment for everyone, and moderators are here to ensure that happens. If you're put on a timeout or a ban, please talk to the moderators in Discord. They're not here to stifle chat. They're here to ensure you get an opportunity to learn and ask questions, and I really want you to ask as many questions as you have. But there are a few rules with the questions. First, we ask that you ask your questions once and only once. The moderators do see your questions and will send them to me. Now, I may not answer them right away, so sometimes I may save it till the end of the stream if it's not really on topic, or if it's on a specific topic that I'm going to cover in a few minutes, then I'm just going to wait till later in the stream to answer that. But we do see them. The moderators will put it up there, and I do have an eye on those questions here. I'm not watching chat, though, because the moderators would be upset with me. Second, there are just some questions I can't answer on stream, such as, there's something wrong with your Python script or Python installation or something like that. So if you do have a question like that I'm unable to answer on stream, you can ask in the Python study room on Discord. You can either do it while the stream is going on. There's some people that watch that, and they'll be happy to help. If it's after the stream, I have it notification set up, so I'm happy to jump in and answer questions. One of the things I've found, though, is that there's so many great people on the Discord that are willing to help that the answer is usually provided before I can get to it. So it's a great place to ask questions and get feedback. Just a reminder that all the content in this series is based on my Intro to Computer Science course. There's no prerequisite experience or knowledge. We're going to be using basic math examples. We've already hit most of that. So if you're math phobic like most people, you should be good to go. All the content is available on a GitHub repository. You can do !Intro to Python. You can see all of the notes I have that I use, kind of my lecture notes in a Jupyter notebook. There's supplementary resources. So I mentioned this to someone last week. I have a document in there that is supplemental resources. So they are other books online, videos, tutorials. I can't vouch for them 100%, but when I made the list, those resources were pretty good. So that might kind of help you filter out some of the less than desirable material on the internet. So those were pretty good when I looked at them. I've also got some exercises. So if you're having trouble coming up with ways in which you can apply what we've learned, I've got some sample exercises. Some of them are kind of taken from the book. Some of them are modifications that I just built over the years. So happy to answer questions on any of those. Also, the book is linked there on the GitHub. It's Think Python. You can download it for free as a PDF, or you can buy it from your favorite bookstore. Again, I'm not affiliated in any way with the author. I just really like his work, and I find it fantastic that he provides it for free. So let's get down to the algorithm of the week. So let me get over here. So this week's algorithm was determine if a given string is a palindrome. So for those of you that don't remember what a palindrome is, it's a word that's the same forwards and backwards. Level, race car. So those are palindromes. And so again, we've got our four parts of the algorithm here. First one is defining the problem. Again, these problems I give you at this stage are so very simple that we can just restate that I basically give you the problem definition. Now, as you get to more complicated problems, they're the dreaded word problems that everyone hates, where it's a couple of paragraphs. And so figuring out exactly the problem to solve is a little more challenging. Here, it's pretty straightforward. Now, we do have a little bit of leeway here. So we can check this, we can work this so that it only works on words, or we could do phrases. And if we do a phrase, we have to ask, are we counting spaces, right? And so usually if it's a phrase that you're checking to see as a palindrome, you ignore, punctuation and spaces and things like that. So we'll go with a phrase. Basically, it's the same sort of algorithm. We just do a couple of things to the string before we get started. So just know going into it, we're going to accept phrases. So whatever kind of string we're given. So the preconditions, remember, these are the things that must be provided, or the way the environment needs to be set up before we execute our algorithm. So in this case, we're given a string. Now, as with others, we have to have a couple of, we have to consider some edge cases. Do we allow an empty string? So basically a string with no characters. Well, we could say that's a palindrome because it's the same forwards and backwards. So there's not really anything to legitimately say, okay, we can't. So we're going to go ahead and allow an empty string. So I'm going to go ahead and note this. And this is one of those things that it's good to note some of your assumptions, because you don't want to just have it implicit in there, because someone else may read this and not get that implicit assumption. And so a post condition, so I'm going to use the term that we used last week. So we had the new data type, a Boolean. So I'm going to use the Boolean here, true, false. So post condition is, I'm going to write it like this as a function. Excuse me. That the post condition is we return true if the string is a palindrome, otherwise return false, right? And so we could have rephrased that to say we return false if it isn't a palindrome, but this is usually kind of the syntax I've standardized on. It's also very much the standard syntax of Java in their Java comments. And so for 17, 20 years, something like that, I programmed in Java a lot. So I've read through that documentation, so I've kind of taken that on. Again, feel free to come up with your own way, but be consistent. All right, so we've got a couple of things here. So first of all, if we're going to allow any type of string like a phrase, but we want to ignore spaces and punctuation, then the very first step we need to do is remove any spaces and punctuation. All right, so that's the first step. So we just remove that out of the string. So all we have are letters, potentially numbers, that we can check. All right, now in this particular one, we need to start off and check some of those boundary conditions, right? Like an empty string. So we're calling an empty string a valid palindrome. All right, so we could do, like we talked about last week, we could do an if statement here, where we could say if the length of the string is greater than some number, then we're going to check to see if it's a palindrome, right? So if it's an empty string, well, that's a palindrome. But also if it's a string of a single character, like the letter A, that's also a palindrome. So what we really want to check here is to see if the length of the string is greater than 1, then we're going to do something. And then when we say otherwise, here, it is a palindrome, right? Because it's a length of either 0 or 1, which we're defining as already a palindrome. All right, so we can go in here, and there's a couple of different ways we can do this. So we can do an iterative solution, which we've talked about, right, where we go through step by step. We could also do a recursive solution. And then there's a sneaky solution that students have come across. So I'm going to go with a sneaky one here, or a clever solution. Go with it real quick, and then we'll do a more standard approach. So the clever solution my students had would be create a copy of the string and then reverse it. And then all you have to do is compare the original string to the reversed. Because, I mean, if that's the definition of a palindrome, then you just create a copy, reverse it, and compare them. If they're the same, yes, it's a palindrome, right? So this is one of those where if you know your tools, in this case, the Python programming language, if you knew how to do this, then this would be really easy to solve. And so that's one of the benefits of knowing your tool, right? And when we get into strings, we'll see that this is pretty straightforward. But I'm not going to do this way. I'm going to do a little bit more of a traditional approach, just so we can kind of see the thought process. All right, so there's a couple of different ways. Like I said, there's an iterative and a recursive. So let me kind of walk through what the iterative and the recursive would be before we write it out here. So the iterative would basically be, we check the first and the last letter in the string. If they're the same, then we go on. So we then go to the second, and then the second from the last, and compare them. And then if any point we find that it isn't a match, we know it's not a palindrome. So if you remember from last week, what we're basically doing is we're assuming success. We're assuming it is a palindrome until we find something that says, no, it's not. All right. And so iterative is we can just walk through those indices. If we were to do it recursively, we would take the first and the last, compare them. If they're the same, then what we do is we shrink the string to remove the first and the last, and then call the same function again. And so now we can keep on checking the first and the last. And our base case would basically be when we get to a string of length 1 or 0. All right. So since we do a lot of iterative solutions here, and we'll probably do some in the coming weeks quite a bit more than recursive, I'm going to go with a recursive solution. So what we're going to do here is we're going to get the first and last characters in the string, right? And then compare them. And then, so we can say if they are equal, then what we're going to do is we're going to remove the first and last characters, and then pass the new string, so the one without the first and the last, to the same function. We'll go ahead and say it's a function, right? And I'm going to change the formatting here so it's a little bit easier to read what's going on. All right, so I'm going to put basically make a recursive call here, so we know that this is a recursive call, right? If I can say otherwise, not a palindrome, right? And so the idea is we're going to keep going here, and this is going to be our base case. Usually we put the base case first, but it doesn't matter as long as it's executed. So the idea here is we're going to run through. So let's start off with the word level, since it's short. It doesn't have any spaces or punctuation. So the length of the string is greater than 1. So we're going to get the first and the last letters, which are L's. We compare them, they're equal. So we're going to remove the L's. So we have the word Eve, E-V-E, and then we're going to make a recursive call. So we go up here. There are no spaces or punctuation. The length is greater than 1. We get the first and the last letters, which are both E's. They're equal, so we remove those. So we're left with just the string with the letter V. We make a recursive call. There are no spaces or punctuation. The length is not greater than 1, so it's a palindrome, right? If we did car, for example, we pass it in, it's greater than 1, we get the first and the last letters, it's a C and an R. They're not equal, so it's not a palindrome. So we've run through a couple of use cases. Obviously, we need to do something a little bit more complicated, a couple more tests to be more confident. But at least as a first pass, this algorithm sounds like it's good and it's acceptable. Now, we'd have to go into more detail, and then there's implementation challenges and things like that. But as a first pass for an algorithm, it looks to be okay. All right, so there's the algorithm for this week's challenge. If you had something else, there's more than one way to do it. I mean, I mentioned 3 just on stream here. So feel free to post them in the Discord. Happy to take a look. Again, a lot of these, there's more than one way to do it. So that this isn't to say that this is the only way to do it. So this is just a way to do it. All right. So let's get on to Python. So if you remember last week, I gave everyone a homework assignment. Since, I'm still a recovering professor, I still have to give homework. Just be glad I'm not giving tests. So for the Fibonacci sequence, so the idea was we had the 0th is 1, 1 is 1. Basically, it's you add these two numbers, and then it's the next one. And then you add these 2, and it's the next one. And this was the equation for that. Right? And so I challenged you to create this function and implement it. So we're going to do a test here real quick, because I really like this problem, and there's something I want to show about this. So I'm going to go ahead and put some test cases in here. And so, for example, Fibonacci of 5 should be 8. And we'll do a couple more here. We're going to do Fibonacci of 8 should be 34, and Fibonacci of 10 should be 89, right? So obviously I'm going to run it now, and it's going to do all the other stuff. Oh, we've got the year. I'm going to quit that. I don't want to input that every time. Okay, so you go through, and it's got zeros here. All right, so I'm going to do something here so we can see the output a little bit better. Okay, so let's start writing it. Well, the nice thing is this algorithm right here, this definition, will define our algorithm for us. So we can just start writing this. So we can say something like, if 0 is equal to n, then Fibonacci equals 1, because we've defined it right here, right? So this is going to be recursive. So these are base cases, right? So we can then check to see 1 is equal to n, then that's also 1. And the last one here is where we're going to make the recursive call. So we have Fibonacci equals, calculate Fibonacci of n minus 1. I'm going to remove the spaces. Even though I usually put spaces in there, we're going to run out of room here if I don't put spaces, or if I remove the spaces. So, and then n minus 2. So the idea here is we've basically taken this mathematical definition and turned it straight into code, all right? And I should be putting comments in here, but we've got it right up above and I'm talking through it. So I'm the teacher here, and I can bend my own rules. So we've got it, we've followed the definition. So these are our base cases. So I will go ahead and at least put base case 1 in here, and base case 2, and then the recursive call. All right. So what this is going to do is, if it doesn't hit any one of these, it's going to make a recursive call to calculate the Fibonacci of n minus 1 and the Fibonacci of n minus 2. So basically the n minus 1, the n minus 2 to get this Fibonacci. All right, so let's run it here and see what we get. So we get 8, 34, and 89. Fantastic. We've done, 3 of them here. and it looks good. So I want to try it out though. So, being the inquisitive person that I am, I want to try out some other numbers. Let's go something a little bit bigger. So let's try 30. And I don't know if you noticed, but it hiccuped there a little bit. It paused for just a second. All right? So that's a big number. Let's try another one. Let's try 40. It's still thinking about it. Okay? And I don't know if you can hear my computer, just the CPU fans just spun up because it's chugging pretty hard on this. Now you might think, this is a really simple program. What's going on? I mean, it's not that many lines of code. It's this. Well, the challenge is, there it spits it out. I'm not going to do it because I don't think Neil would appreciate me having stream, be idle for 25 minutes when I did Fibonacci of 50. I've done it in class before, and it takes about 20-25 minutes. And it's not really a function of how fast your computer is. It has to do with something called computational complexity, which is about as close to math as you can get computer science. And there's a reason I wasn't a math professor. So basically the idea is, this is technically correct, which, if you've watched The Simpsons, that's the best kind of correct. But it's a very poor solution, because every recursive call we make here isn't one, it's two recursive calls. So if you were to look at it, this first one here, we have two recursive calls for Fibonacci of 2. When we go to Fibonacci of 3, we have to calculate Fibonacci of 2, which is two recursive calls, and then 1, which isn't a recursive call at all. And then when we do the Fibonacci of 4, we have to do Fibonacci of 3, which is all the recursive calls involved in that, and then the recursive calls involved in 2, and so on. And so the idea is that this just explodes computationally. So basically, every time you increase the number by 1, so increasing from Fibonacci of 5 to Fibonacci of 6, you double the size of the problem. So if you can imagine, we're getting up here on complexity to 2 to the 50 calculations on the order of. So this is, in computer science terms, it's 2 to the n, where n is this number. So every time we increase it by 1, we're doubling the size of the problem. So basically, I don't want to go off the deep end here, but the idea is, while there are correct ways to write programs, they're not necessarily the most efficient. Right? Now, at this point, we're not worried about efficiency, but if you're writing Python scripts to process large amounts of data, you do have to worry about this. So this isn't because that we elected to solve this recursively. It's because in this particular formulation, there's two recursive calls. So I just want to warn you of this. It's not something to dive into at this point. For all the stuff you guys are writing, probably at this level, you don't have to worry about it. But should any of you try and do something with large amounts of data, you do need to worry about this. And so you'll have to investigate efficient ways of doing it. The nice thing is, if you're using libraries, most of the libraries already account for this. But if you're writing your own code, then you have to investigate other ways of figuring out what to do. So, I'm going to stop there because I'm probably getting too geeky on that stuff. But if anybody has any questions or wants more information, I can dive into it more. There's images on the internet that show that sort of thing, and I'll drop it in the Discord so you guys can see what it's like. All right, so just something to think about. If you want to take this code and run it on your computer and see what happens, go for it. I always had my students do it, and just to kind of see how long it would take on their computer. All right, so that's it with chapter 5. There's some more we could talk about when we go through that with recursive functions and things like that. But I think we've illustrated the point. If you want to work through the exercises, I'm more than happy to help you with that. So let's move on to chapter 6. So chapter 6, we're going to dive into functions more. And this chapter focuses on fruitful functions. So this is what the author calls functions that return a value. So most of the time, so when we first started writing functions, they didn't return anything. So remember, they just printed out values. And so functions that don't return a value are void. So Python calls it none. All right, we've got a question real quick before I dive into this, since it was on the Fibonacci problem. Emmanuel's asking, it's not very efficient because it's an exponential function, right? Yes. So this is called, I'm going to go ahead and write it just since there is a question, you gave me an excuse. Something called Big O notation, and it talks about computational complexity. It's the upper bound. And so, yes, it's exponential, meaning that every time, in this case, every time we add one, it doubles the size of the problem. There's others that aren't quite as bad, but all the really interesting problems in computer science are the really nasty complexity ones, which is why things like cracking passwords and stuff like that, the more you add to it, it just increases it, the complexity and the amount of time it takes to solve. So that's, basically cryptography is based on the assumption that they're really hard to solve. And then once you get quantum computers, it throws it all out because they compute things differently. So, but I won't get into that. But yeah, it's an exponential function. All right, so back to the fruitful function. So if a function doesn't, if you don't specify a return statement, it returns void. So other programming languages, so C, C++, Java, things like that, you'll have a void function. In Python, you don't specify it, but when you don't return anything, the function actually does return something. Python will always return it. It will just be none. So none is a special Python keyword for nothing. Other programming languages will say null, something like that. But Python, it's none. So if I were to do something like this, I would have a function called test_me that doesn't do anything and prints hello. And so I could, if I wanted to, call test_me and then print out the result. And it's going to say none. All right. And that's because this isn't a string. It's actually a value just meaning nothing. Okay. So I don't have a return statement there. And so it just returned none. All right. So we've done some functions already that have return statements, but I want to point something out to you here. That is something I see people new to programming do quite frequently, and it's one of those things that it's technically not wrong, but will cause problems down the line. So I'm just going to write some code here real quick, and it doesn't really do much, but it's not solving a particular problem. It's just code to demonstrate something. So I'm going to do something complicated. So basically assume that we're doing something here. So I'm just checking to see some values. Return 1, and then else return 0. Okay, so the idea is, assume there's something more complicated going on here. What it's actually doing isn't important. The point here is we have multiple return statements, right? Now, this is perfectly legal in Python and many other programming languages. So don't think that I'm saying that it won't run. So if I were to run this here real quick and call it with, do something multiple, meaning multiple times, or multiple return statements, and I called, 5, and print it out, it's going to go and it's going to return the 0. So it's perfectly legal code. The challenge is if I were doing something really complicated in here, and so assume that I'm doing something complicated in here as well. Assume there is a bug, right? That it's not working properly. It returned a 0 and I thought it was supposed to return a -1, right? I now have to put debugging code in 3 different places because it could be returning at any one of these places. And so I have to create duplicate code in multiple places, right? Because there are 3 ways I can get out of this function. And so I have to account for all of those. Whereas if I do something like this, I'm going to copy and paste. So I'm going to call this do something single. And then I can just put the result here. I'm going to call it 0. And instead of return, I just store the value in here. And then down at the very bottom, return result. All right. So all of these are equivalent, or both of these are equivalent, right? At this point, assuming I get it right, which, last week I demonstrated my ability to screw things up, that assuming I get everything correct, these are equivalent functions. However, if this is non-trivial code, the odds of screwing something up is pretty high, especially for me. So what I have found is I have one entry point into the function, and I have one exit point in the function. So if I need to debug what's going on, I can put debugging code up at the front and debugging code at the end, and I know that I'll be able to catch it. I only have to do it once. All right. This may seem like not a big deal to you, but once you get to the point where you program quite a bit and these functions can get complicated, trust me, tracking down a bug is challenging. So I've heard it described, and I really believe it, that it takes 50% more intelligence to debug code than it took to write it in the first place. So by that definition, if you write code as clever as you can using all of your intelligence, you're not qualified to debug it, right? And debugging code is hard. So if you make it simple and easy to debug, trust me, you'll thank yourself in the long run, right? Making easy to maintain and debug code is really essential. So I'll go ahead and say it again with the comments. Pretend that the person coming after you and having to maintain and use your code is a homicidal maniac that knows your home address, right? You want them happy with you. So doing this sort of thing may seem like something simple, but trust me, as you go, being able to debug something like this is a lot more beneficial and saves a lot of time in the long run. All right. As we're writing these functions, so, I've got to do something complicated. Hopefully at this point, you've kind of seen sometimes, so I did this in the Fibonacci. I wrote a little chunk of code, tested it, and then did some more stuff. So this is what's called incremental development. And so if you look at the lecture notes that I have as a Jupyter notebook on the GitHub repository, I dive into this more. And I don't want to do like lecture slides or anything because I'll fall asleep with that too. But the idea here is when you're working on a program, you don't go write everything and then run it to test it, right? Because inevitably you're going to find a problem and then you're going to have to track down where it was, and it could be anywhere in that function. So the idea is you take a little bit of code that's functional and then you add something new to it. So add a couple of lines, then you test it. Add a couple of lines and test it. And so if any point something fails, you know more than likely it was in that little bit of code that you just added. All right. And sometimes as you do it, you're going to add code that's called scaffolding code. So you might have seen it as we've gone through on some of the others, where I may print out a statement here, some values there, just to kind of see, am I on the right track? Are things going right? Right. That's called scaffolding code. It's not going to be there at the end. It's just there to help you. So like when they're building a high-rise building, so it's all the scaffolding that goes around there. They're going to take it down when they're done building the building, but it's there as they're building to help make the process easier. The same thing with code. So, and then sometimes that scaffolding code, you may not want to delete it. You could just comment it out. I've done that before. If it's still under heavy development and some things may change, keep it in there. Once it becomes kind of rock solid, you can delete that. But the idea is that code is there to help you write it, and then you can remove it later. All right. I also talk a little bit more, and the book talks about composition, using functions, existing functions to build other functions. We already talked about that in a previous example where we did that App Store in Chapter 3 of the book. So you can go back to the previous stream where we talked about that, about building functions with other functions. So that's pretty important. I want to make sure that you understand that. So I'm not going to spend time on today's stream, but if there's questions, I'm happy to answer them on that topic. But if there aren't any questions, then I'm just going to go on here. So, another type of fruitful function. So we talked last week about Boolean data types and Boolean functions or Boolean expressions. So we can, very common to have Boolean functions. So these are functions that return true or false. And most of the time, these functions are asking simple questions like, is this number even? Or is this number in between these values? And so remember way back in the beginning when I was talking about naming conventions, right? Everybody's favorite topic. I said variable names are usually like nouns, and functions are verbs. They do things. And so when you have a Boolean function, one of the things I really like to do is make it asking the question. So make the function name asking a question. Makes it really easy to understand what it's doing. So for example, I can say is between, so basically saying is y in between x and z. And so I can, is y between x and z. So what I can do is now I can write code. And so I could do it in one statement if I wanted to. I could say, so that x is less than or equal to y, and y is less than or equal to z. So in this case, it's between, right? Now, you don't need this last set of parentheses. It will work fine without it, but I'm, a defensive programmer, and so I put that in there to make sure that it'll always work. All right, so if I were to do things like print is between 1, 2, and 3, so this one would be true, right? Because 2 is in between 1 and 3. So I get a true, and then let's try one that's not that case. So 55 is definitely not between 1 and 3. So I run that, and it's going to be false, right? So again, nothing super special, but it's just how do you name your functions, and in this case, ask a question, right? Now, this brings up a very good point here. So, for example, if I'm wanting to write code that then does something, because this is a Boolean function, right? So we talked about Boolean expressions are used in conditionals or if statements. So the idea is people will write code that says, if it's between this, then do something. So, for example, I could say is between 1, 2, and 3, and then I want to make sure that that is true. And I can say, yes, it's between. All right, so I run this, and it's between, and everyone's happy except for me. And it's because we're testing that it equals true. This is already a Boolean expression, right? Do we really need to test true equals true? No. Right? I see this all the time in new programmers. They feel that they need to test this. So let me don't do this, because this is much better, right? If it is between, that's going to be true or false, right? This is unnecessary. And to be honest, if you've got code out there that's like this, people who've been programming for a while, may kind of look down their nose at you. And it's not necessarily being snooty. It's that you're not experienced enough to understand that, it's unnecessary. And so it could be kind of a gatekeeping thing, but one of those, if you can, avoid this, it makes you look like you're a more experienced programmer. And it shows that you kind of understand what's going on at a little bit deeper level than just surface. So, don't do this. You can also do, so for example, if you want to do not between, you could just put a not in front of it. And so you change that so it's not between, right? Sometimes it is easier, or it's better to put the not in here than something more complicated, because if the problem statement is such that you're actually wanting to test that it's not in between. So for example, let's see, what would be a good example? If university, right? If you're between certain hours, you can enroll, right? So juniors can enroll right now, but not freshmen and sophomores and things like that. So it's easier to maybe put up an error message that says you can't enroll here if your hours aren't in between the two limits for a junior, something like that, right? So in that case, you really want to test if it's not between those. And so you've already got a function that's easy to test. Is it between it? And then you just not it, right? So, and again, this is more of a people reading code thing rather than a computer reading code. So never underestimate the importance of your code making sense to people who are reading it, right? So again, just a simple thing with, Boolean functions, all right? So let's run through a couple of examples. So the concept of fruitful functions we've already kind of seen a number of times. So I don't think that it's necessarily that complicated of a concept. I do think that the single return statement is one of the things that gets most people, followed by the equals equals true or equals equals false. So I want to run through a couple of examples on how we would write code. So for example, let's say I have a problem that I want to sum the integers from 1 to n. And I'm going to say inclusive, which means I want to include n in that. All right? So we've got to kind of think through. So I'm going to kind of take my own advice and let's walk through what it would look like to come up with an algorithm for this. All right? So I think we've already even kind of talked about it before. So we're going to start off here, and I'm going to just go ahead and create a function. And let's solve this one iteratively, right? And then we can do another one with it recursively and see how it's different. All right, so the first thing, if you remember, I've got to have a number to store it in. So it's going to, we'll call it the total. So we want to define a variable total to hold the total value. That's why we called it total, right? So we're going to do that. So if it's iteratively, we're going to have to walk through the numbers. So we're going to have to iterate through the numbers 1 to n, right? So that was in our problem statement. And so then whatever our current number is, we need to add the current number to the total. And then when we're done, we can return the total. So let's think about it here real quick to make sure we've got it all, right? So we're going to start off with a variable total that's going to hold it. And then we just iterate from 1 to n inclusively. So we make sure we get that n in there. and add it to the total, right? So if I want to sum the numbers from 1 to 3, so I've got to add the 1, then the 2, then the 3. So I add 1 and the total is 1. I add the 2, the total is 3. And I add the 3, so the total is 6. Right? So kind of in that little thought experiment, the algorithm works. So let's start writing code. So I've got total equals 0. Iterate. So remember, this is going to be a for loop. So for I in range. Now, when we first talked about range, we just gave it the stop value. But notice here on the screen, I can give a start value. So I want it to start at 1. I could let it start at 0, and since it's addition, it won't make any difference. But let's be intentional here. And now, if you remember, if I were just to give it n, it would actually stop at n minus 1. So it won't actually get the n. So to get that value n in there, I actually have to add 1 to it. So I say range 1 to n plus 1, it actually will stop at n. Right? So let's write some scaffolding code here, kind of practice what I preach, and see what's going on here. So let me write code here to run this. Some numbers iterative, and I'm going to go ahead and use my example of 3, and so that should be 6 when we're done. Right? So I run, and it prints out none. We go and we go, oh, well, that's not working. It's because I'm printing out the wrong variable, right? You go, oh, okay. I need to be using I. So I is in here. And so this is the benefit. If I had gone and written all this code, this error, I would have had to track down this error in a lot more code. Now, I just have this little bit of code and I can test it and go, okay, it's doing 1, 2, 3. Now, the answer at the end isn't right, but I'm not worried about that right now. I'm just worried about, is this portion of code correct that I wrote? So I can say, okay, that's working. So now I need to add to total. So there's a couple of different ways to do it. So I can say total equals total plus I. But, and the book talks about this too, I don't remember if it's in this chapter. Remember, computer programmers are lazy. I'd rather spend, a couple hours writing a program to do something for me than, 30 minutes to actually do it. So I'm too lazy to write out total here twice. And so I can write plus equals. And so basically what this means is take total, add I to it, and shove that new value back into total. So it's the equivalent of this. So I'm going to use the shortened version here, right? And so I'm going to go ahead and print out total here. As another test. Remember, this is scaffolding code. So I can go through 1, and then I add 2 to that, so it's 3, and add 3 to that, so that's 6. So at this point, I think we're good. So now we can return total. So and now I can comment these out. I'm going to leave them in here for the moment because it looks like everything is working. All right, I get 6. So let's see, if I were to do this for 5, it should be 15 because a 4 and a 5 on here. And I've got 15. All right, so I've got some confidence that it works, right? I haven't proven it, but I've run it with a couple of them, and I've got confidence that it works, right? So that's kind of the process of incremental development. Now, let's do the same thing, but with recursive function, right? So I'm going to do def sum numbers recursive n. All right. So I'm going to start off with the exact same thing. And go with this. Now the question is, the next one, we're not going to iterate, right? So the question is, how do we solve this recursively? Well, there's a couple. We've got a number. We start off with n. So what we could do is we first have to check to see what our base case is, right? So what's our base case? Well, we know we're going to stop at 1. 1 is the smallest number, and n is the biggest number. Well, we've already got n, so it'd be easier to work from n down to 1 than it is trying to work up since we've already got this n here, right? And so the base case would be, does n equal 1? Or if we want to be paranoid, we want to say, is n less than or equal to 1, right? Because if someone tries to mess with this and throw in a decimal. So we can say if n is less than or equal to 1, then total is equal to 1, right? So if I want to sum the numbers from 1 to 1, well, that's 1, right? So that's going to be our base case. And then we can say otherwise, we need to make a recursive call. So we can add n to the total, and then we've got to figure out what the next one is. So I'm going to actually rewrite this. I'm going to do the n here first. We're going to have to figure out what the total is of all the others, right? So we've got to figure out what the total is, the sum of the numbers from 1 to n minus 1, and then add n to it, right? So we need to calculate the sum of numbers from 1 to n minus 1. And once we know that, then we just add n to that total, right? I mean, that's essentially what we were doing up here. So that's going to be the recursive call. And then once we're done, we're going to return the total, right? So we're going to walk through it here. There's a question from Just Ben. Is there a preferred method among programmers using long versus short? Oh, short. We're lazy. We're going to take any shortcut we can. Yeah. So there's actually a term for these sorts of things. They're called syntactic sugar. Sugar makes life sweeter and it kind of makes it enjoy it more. You don't have to have this. You could do it without it, but it just makes it nice. So this is called syntactic sugar. So all programming languages have some syntactic sugar. You don't have to have it in there. You can do without it, but it makes it nice. So, all right, we have total equals 0. I've got an if statement. And if you notice, these comments of the algorithm, or the algorithm statements, are comments for code, and it really helps to write the code, because in some cases like this, it's going to tell me exactly what to do. So total equals 1. And then I can say else. All right. So the total, in this case, is the sum of numbers from 1 to n minus 1. So I need sum numbers recursive to n minus 1. And once I know that, then I can add n to it. And remember, every time I call this, since I'm calling n minus 1, it'll go through however many times I need to, and then stop at the base case. And so then I can return total. Now I'm going to try these exact same tests here because it's the same problem, so the answers should be the same. It's just we're going about it and solving it in a different way. So I run this. Notice I get 615, 615. So the answers are the same, which is good, as it should be, right? The solution should be independent of the way we go about it, right? So we've chosen 2 different ways to solve the same problem. Now, in this case, I'd go with the iterative solution, right? It's much easier to understand, so it has a lower cognitive load. I don't have to think as hard. It's easier. It's going to be more efficient, but at this point, we really don't care about stuff like that. But both of them are equally good, and there's not really a real efficiency problem because it's single recursion here. All right, and this illustrates an important point. So if we go back to a previous episode, we talked about composition and abstraction. So I think it was on the chapter 4 one, or not abstraction and encapsulation. So abstraction is pulling away from the details. So here we're pulling away from the details of exactly how I'm doing this, right? They're different function names, but I could call it sum numbers and be fine because they both do it. So I've abstracted away from the details that I just call a function and it does it. And I've encapsulated it. I've wrapped it up in this function. So the idea is If I started off with a recursive implementation and later wanted to change it, I could go back and change it. And as long as I don't change the name of the function, right here we've got it, but imagine if we didn't have it on here, or the return value, or anything about that contract, or the prerequisite or the preconditions and postconditions, as long as all we're changing is the guts, anyone who calls the function doesn't care. So that's a real benefit, that if you find a better way of doing things, or you fix a bug and it's all wrapped up into a function, you get the benefit of that function, that you can change that, and then the people who call your function don't care about it, that there was a functional change. They may see a benefit, it may work more efficiently, or it may actually be correct and not have bugs, but they don't have to change their code. All right, so both of these are equally good. The iterative was probably a little bit easier to write and easier to think about. That's not always the case. Some problems lend themselves to recursive. Some problems lend themselves to an iterative solution. It really depends on the problem. And hopefully you've seen from this that you can take a recursive algorithm and switch it into an iterative, and go vice versa too. You can take an iterative solution and make it recursive. So they're equivalent. It's just what makes the most sense. So there have been times where I've just written a recursive solution because it makes more sense given the problem. There's sometimes where I've written a recursive solution, it makes more sense, and then I realize it's not that efficient. And in this particular case, it was something I was running on a supercomputing cluster, and efficiency would actually make a difference. And so I go back and rewrite it as an iterative solution. That sort of thing happens. It's fine. Just go with the easy one first and then worry about efficiency. All right. So that's about all that I have for today, this evening. If you look through the lecture notes that I've got, there's some other things that's talked about in the book that we may touch on a little bit in next week, but they're not real important concepts, and they're pretty easy to see. So take a look at it. Again, if you've got questions, throw them in the Discord chat. So I'm going to wait a second to see if there's any more questions coming through before I end it. So remember to check Twitter by every Monday, because I'll post the algorithm of the week. I'm happy to answer questions in the Discord. I see there's a question coming through, so I'm going to try and just stream of consciousness for a second. All right. Emmanuel said, in the recursive solution, why is there a total equals 0 statement? All right. That's a great question. So I've got a couple minutes here. If I didn't have this in there and tried to run it, it would technically work in this case, but some programming languages, sometimes it really won't work, because if, for example, there was a situation where I didn't create this variable, it would be an error. So, in some ways this shouldn't work, because I'm creating a variable inside an if or an else statement. It shouldn't exist outside of this if I create it here. But the idea is we create it first so we know it exists outside of this if statement. It worked here. In other programming languages, it will not. So I can tell you for a fact that in Java and C++, as long as you're using a standard compliant compiler, C, things like that, this will fail on you, because if this line isn't here, the code doesn't know about this total function or this total variable. So what we're essentially doing is we're defining it at this level. It may be a case where this is not an else. If this is an else if, then I may not hit or get any one of these true, and so I need to have a default value. So the idea is we've defined it up front so we know it exists when we're going to return. We avoid any gotchas, things like that, and we can set a default value. All right, so it's good programming practice. And again, there's some things that in one programming language it would allow you to do. Other programming languages it won't. And so when you program in more programming languages, one of the things you'll definitely want to get in the habit of is programming such that it works in a wide variety of languages, so you don't have to change the way you think when you go to program in a new language. All right. So thanks again for joining us this evening. I hope it's benefited you. Ask questions in Discord when and if you have them, and I'll see you next week. Bye.